Solving applied problems involving rational functions. In example 2, we shifted a toolkit function in a way that resulted in the function f of x, which is equal to 3x plus 7 over x plus 2. This is an example of a rational function. A rational function is a function that can be written as the quotient of two polynomial functions. Many real-world problems require us to find the ratio of two polynomial functions. Problems involving rates and concentrations often involve rational functions. A rational function is a function that can be written as the quotient of two polynomial functions, p of x and q of x. So f of x is equal to the polynomial function p of x divided by the polynomial function q of x. Now for example number 3, we're solving an applied problem involving a rational function. A large mixing tank currently contains 100 gallons of water into which 5 pounds of sugar have been mixed. A tap will open, pouring 10 gallons per minute of water into the tank at the same time sugar is poured into the tank at a rate of 1 pound per minute. Find the concentration pounds per gallon of sugar in the tank after 12 minutes. Is that a greater concentration than at the beginning? So at the beginning, so if we know that 12 minutes is t after 12 minutes, right? Then at the beginning, that means that t would then have to be equal 0 minutes. Okay? So we want to make sure that we can identify what that is. Now, we're going to let t be the number of minutes since the tap opened. Since the water increases at 10 gallons per minute, and the sugar increases at 1 pound per minute, these are constant rates of change. This tells us the amount of water in the tank is changing linearly, as is the amount of sugar in a tank. So we can write an equation independently for each. So, if we take a look at the first sentence here, it's saying that the large tank contains 100 gallons of water into which 5 pounds of sugar have been mixed. Okay? And that means that it's pouring at 10 gallons per minute of water. So this is the rate, and this is what's inside the tank. So the water, W of t, is going to equal 100, which is what is in the tank, plus 10 times whatever t minutes there is in gallons. So that is our first equation. Now our second equation is we're dealing with the sugar. Now sugar, okay, is the 5 pounds of sugar here that's been mixed. And that 5 pounds of sugar is being poured into the tank at a rate of 1 pound per minute. So the sugar, S of t, is going to be 5, which is the fixed, plus 1 t in pounds. So now we have our two equations. Now the concentration C will be the ratio of pounds of sugar to gallons of water. So C of t is going to equal 5 plus t, which is our equation for sugar, divided by the equation for water, which is 100 plus 10t. Now that we have our concentration because it's being mixed, then we want to figure out, okay, what happens after 12 minutes? So after 12 minutes, what we're going to do is we're going to substitute t is equal to 12 into our rational function. So if we plug in 12 in for t, we're going to get 5 plus 12 over 100 plus 10 times 12, which gives us 17 over 220. So what does that mean? This means that the concentration is 17 pounds of sugar to 220 gallons of water. So in step 4, then we need to figure out what's happening at the beginning. And that means the concentration at when t is equal to 0. So now we're going to plug in 0 in for t. So we end up getting 5 plus 0 over 100 plus 0. 5 over 100 reduces to 1/20, which means that the concentration here is 1 pound of sugar per 20 gallons of water. Now, if we find the decimals for both of those, 17/220 is approximately 0.08. 1/20 is equal to 0.05. So we can see that 0.08 is greater than 0.05. Therefore, the concentration is going to be greater after 12 minutes than at the beginning.